Hey class, I had to put today's lecture online today. I'm out of town, but today we're going to talk a little bit about feedback and feed-forward systems and different types of control theories. So three different types of control that we have is that we have feed-forward control, which is evidence from catch or people trying to catch something, so we call them catch trials. Then feedback, which is from subjects eventually getting to a destination of reach. We've talked about, using feedback, using structures and tactile signals, using vision, and making adjustments to our movement based off of feedback systems. And then we have impedance control, which we'll talk a little bit more about, basically stiffening the arm to resist any type of perturbation. We'll go into more detail of that in a little bit. So feed-forward system is kind of a prediction type system in which we're sending a signal that readies the system for the upcoming motor command or readies the system for the receipt of some type of particular kind of feedback or both. So it involves the delivery of information to some other part of the system to prepare for incoming sensory information or for an upcoming motor command. So it serves as an important role in error detection and correction, often occurring in anticipation of the error. So we see input, system, and output. So a system might include bones, joints, muscles, gravity, wind resistance, weight of an object, so on and so forth. But it's more of an anticipatory type of model in which we constantly try to update based off of practice. And so internal models, the form of a feed-forward model, could be a big component of learning by updating that model. So it can be modified and adapted. It's also known as a open loop control. So basically we kind of make a copy of the movement and store it for the future. And these are now modified and adapted as the environment changes. So these internal models enable the CNS to predict the consequences of motor commands and to determine the motor commands required to perform certain tasks. Now these internal models, they can be transferred to different workspaces, different environments. They're remembered, have a limit to their complexity, obviously. They can be interfered with and usually aren't just dependent on visual information. So we'll look at some examples of some internal models that are feed forward or, as we mentioned, open loop under open loop control, in which we're not using vision or anything. We're using a model from practice that we've developed, say swinging something. We don't do that based off of really much information. We have our general idea of what our swing is going to be. We're then going to swing the bat, and we're going to use a little bit of feedback to also now maybe correct mid-swing if that ball moves. So feedback control is usually slow. It's a closed loop system, closed loop control. So the knowledge of movement used to make corrections to ensure accurate performance during the movement. So here you see the CNS to the muscle to the limbs, joints, and environment. We get some feedback from vision, proprioception, touch, which then gives us hopefully a good output. So feed forward versus feedback. We have internal model adaptation, which requires information from previous trials to refine the internal model. So this is the feed forward. It occurs after the performance of the motion. So you might think of someone who consistently does something and then makes adjustments. Would be an example of updating the internal model or internal model adaptation. Feedback control occurs during the actual motion. So consider pin the tail on a donkey not blindfolded versus throwing a dart. One being more feedback, one being more feed forward. So feed forward is faster. As I mentioned, feedback can be a little bit slower. Requires an accurate model though of the environment, but can't really compensate for something new that might happen. Feedback requires an error before a control signal can be given, which causes the delay, typically more accurate, and can actually compensate for unanticipated changes. So these feed forward feedback, they do kind of work together but separate at the same time. So examples of more of a feed forward feedback. So we could think of cruise control, right? It just knows what it's going to do. Our car is going to go 65 miles per hour, and that's just what it's going to do. Prehension with grasping could use a little bit of feedback in terms of how firm we're going to grip. Then a baseball swing, obviously we have a accurate internal model of how an individual's or how we're going to swing. However, we could also use a little bit of feedback in terms of looking at the release point of the pitcher's hand to possibly adjust that internal model of our swing. So impedance control is in which we stiffen our limbs in all directions except the direction of the desired movement. So it impedes movement in an undesired direction. This is kind of a last resort in terms of our control strategy, as it's very energy inefficient. So this would be a very stiff type of movement. So when we're talking about catching an object, we're talking about feed forward control, because obviously we have to anticipate where the ball is going to be based off of where someone's release point is, the trajectory of the ball as well. So there's two critical phases for vision: the initial flight and just prior to the catch. So vision provides information about the movements of objects in the environment, as well as about the movement of one's body in that environment. And much of motor control involves tailoring now our motor behavior to meet these visually presented environmental demands. And then we have spatial accuracy in which we use our vision. Mid-flight, not necessarily essential, because we've already moved based off of the initial flight. Say someone threw it way off to the right, we saw that, so we started to run to the right automatically. Not a whole lot's going to change mid-flight, and then we use some visual feedback to kind of hone in on our target and make any adjustments in terms of where our hand placement needs to be to catch. But how do we determine how we're going to move, or how we're going to catch something, or how we're going to feed ourselves, bring our finger to our nose like we did in the day one of class? We talked about Nikolai Bernstein the very first day of class. So he proposed a degree of freedom problem. So he was trying to figure out, do we explore the range of possible movement solutions as we learn a skill? Because there are several different ways in which we can perform a task, but is it the most efficient? So the degree of freedom problem is that there are multiple ways for humans to perform a task. So how do we select the one that is used, or the best one? So we need to consider, I mentioned touching the tip of your nose. You can do this several different ways. So to give you guys some background, the degree of freedom is any independent parameter of a system that can vary down to the level of a motor unit from the neurophysiological perspective. And so if the information processing system we're involved with is in the production of all the decisions about each of the muscles participating in a motor act, it could be difficult to imagine how this would explain all the mental work involved in producing a simple task. So the main concern with the degree of freedom problem is that the fundamental concern is that the system has too many independent states, so it must be controlled at the same time. So hence the problem. So if you look at this, how many degrees of freedom in just feeding yourself? Well, each of our joints has a certain degree of freedom. There's several different possibilities in which we can move those joints. And so how do we select the best one? So to solve this degrees of freedom problem, we can look at the speed accuracy trade-off and optimal control. So optimal control, we try to optimize something like energy use. So the idea is that we want our bodies to be the most efficient and utilize the least amount of energy. So we can now select that strategy that is going to be the most efficient. And we'll use open and closed loop control to enforce an optimal solution. Then there's the speed accuracy trade-off. Typically what we see is that if we want accuracy to improve, the speed of a movement decreases. If we speed up a movement, typically accuracy decreases. So one of these may be constrained for a particular task in which we're trying to perform, which really limits the number of solutions that we can pick. So moving on to now voluntary muscle activation. So two main ideas of how we actually generate movement. One based off the CNS specifies the level of activity in alpha motor neuron pools. And then the other main theory we'll talk about, the equilibrium point hypothesis. So we know muscles act like they're like biological springs. They stiffen and change length. And for the equilibrium point hypothesis, basically they're saying is that an agonist and antagonist, so think like during elbow flexion is the agonist is the bicep, the antagonist is the tricep, that these muscle pairs have an equilibrium point to which a particular joint would move in a certain situation. And then the nervous system changes the spring muscle stiffness to length and length to shift the equilibrium point as needed. So in the equilibrium point hypothesis, all movements are generated by the nervous system through a gradual transition of equilibrium points along the desired trajectory. So the equilibrium point in this sense is taken to mean a state where a field has zero force, meaning opposing muscles are in a state of balance with each other, kind of like two rubber bands pulling the joint to a stable position. So the equilibrium point is also called threshold control because signals sent from the CNS to the periphery are thought to modulate the threshold length of each muscle. So the EP hypothesis in simple terms points out and states that we program endpoint location of our movement rather than force amplitude or movement at each individual joint. So movements are therefore caused by changes in equilibrium points. One disappears and then another emerges. So how are these set? Could be by altering the stiffness of different muscle pairs, or tonic stretch reflex is thought to be the primary mechanism. So if we want to move our hand smoothly through the air, okay, we define a desired trajectory or path of our hand. Okay, there's a series of equilibrium points created, and then your arm and your hand has a trajectory, which is your actual trajectory, and moves towards that object. There's also a leading joint hypothesis. So we have the endpoint hypothesis. Now we have the leading joint hypothesis. The main idea is that the CNS exploits the biomechanical properties of the limbs for movement organization. Meaning we have a leading joint and then we have subordinate joints. So if we think of it this way for the leading joint hypothesis, basically think of trying to grab something in that the hand is going to determine, so think of the joints of the fingers, the wrist, the joints of the hand are going to tell the subordinate joints of the elbow of the shoulder what they should be doing. And so this is these are the two different kind of hypotheses in which we try to further understand why our body chooses certain movements and movement patterns for different motor behaviors.